Let us derive the torque equation of synchronous reluctance motor. The above diagram, actually directly we will not derive the equation from synchronous reluctance motor. Instead of, we will consider synchronous motor for deriving this equation. Here in this diagram we can see that the rotor, it has rotor field windings, but in actual synchronous reluctance motor the rotor does not have any windings. The rotor does not have any windings. But in order to derive the torque equation, we will consider the synchronous motor. So initially we will consider this synchronous motor, and during the final step we will remove, that is in the final step of the torque equation we will be having two components. In that we will remove that second, we will remove the first component, that is which is related with the rotor, and we are deriving this torque equation with respect to the q axis. And in order to derive the torque equation, we should consider this phasor diagram. In this phasor diagram we have taken the q axis as the reference frame, where del is nothing but the torque angle or power angle, which is the angle between Vs and Vf. Vf is nothing but the field excitation voltage, and Vs is nothing but the stator voltage, and or the supply voltage. Vs may be called as source voltage or supply voltage or stator voltage, and the angle between Vs and Is is pi. And here we have the two components, d axis component and q axis component, where psi suffix a, which is indicates the armature flux linkage, psi f, it is the field flux linkage, psi s, it is stator flux linkage. The stator current, that is the supply current, it has the two components, one is IDS and IQS, which is shown in this phasor diagram. And let us consider Vf is excitation voltage. As I said, psi f is nothing but the flux linkage induced by the field current, and Vs, Is are the supply voltages and current. Psi s is stator flux linkage. This is stator flux linkage when armature flux linkage aids with the field flux linkage. That is what psi s, and pi is nothing but the power factor angle, which is the angle between the supply voltage and the supply current. By delta, it indicates the torque angle or power angle or angle of retardation, which is the angle between the supply voltage and the field excitation voltage. Initially, we will consider the power input to the motor, which is given by Pi is equal to 3 into Vs Is cos phi. Here we are giving the three phase power input, so we will be having 3 into Vs Is cos phi. Suppose if it is single phase supply, the input power it will be Vs Is cos phi alone, but for the stator, not to create the rotating magnetic field, we are providing the three phase AC supply, so the power input will be given by 3 into Vs Is into cos phi. From the phasor diagram, we will obtain Is cos phi is equal to IQS cos delta minus IDS sin delta, and Actually, we have a separate derivation in the next video for is cos phi. How it comes, how we are getting that, that will explain the next video. Now consider that is cos phi, which will be given as per equation number 2. Now substitute the equation number 2 in 1. So in the first equation, instead of is cos phi, you substitute this iqs cos delta minus ids sin delta. Again, consider the portion of the power angle or torque angle triangle. From that, first you should write the cos delta and sin delta equations. So from the phasor diagram, if you write the cos delta equation, which will be given by VF plus IDS into XDS divided by VS. So from that we are writing this IDS equation, which is equation number 4. Similarly, for the same triangle, we are writing the sin delta equation, which is equal to IQS into XQS divided by VS. So if you consider that triangle and if you write the expression for sin delta, you will get it as IQS into XQS divided by VS. From that equation, we are writing the expression for IQS as VS sin delta divided by XQS, which is equation number 5. Now substitute the fourth and fifth equation in the third equation. So in the third equation, we will be having the terms IDS and IQS. So we just replace it using this fourth and fifth equation, and we are writing this equation. So the power input is equal to 3 into VS sin delta divided by XQS into cos delta minus, this minus is common for the entire term, that is VS cos delta minus VF divided by XDS into sin delta. And then we will rewrite that above equation in the following manner. Again, we will use the formula sin delta cos delta, that is sin 2a is equal to 2 sin a cos a. We will apply that equation here in the for the first term, and also for the second term we will separate that equations. So the equation, it becomes Vs into sin 2 delta divided by 2 into XQS, because in the above equation we should multiply and divide it by 2 by 2, so that the equation will be balanced. For the second term also we will do the same thing. So it becomes sin 2 delta by 2, and we will get it as 3 into Vs into Bs sin 2 delta divided by 2 into XQS minus Bs sin 2 delta divided by 2 into XDS plus Vf into sin delta divided by XDS. And then we will multiply this 3 into Vs term, or we are bringing this 3 into Vs term inside this bracket, and we will write that equation. Afterwards, we will commonly take that 2 into XDS into XQS term, and we are writing it as 3 into Vs square into XDS minus XQS into sin 2 delta. That is, we are separating that sin 2 delta and sin delta terms, so which is equation number 6. So actually the shaft power output, which is equal to shaft power output, which will be equal to 2 by P into omega into T. Actually we know that the power output equation of a motor, the output power will be in mechanical energy. So P naught is equal to 2 pi nt by 60. Ns is nothing but the synchronous speed, which will be given by 120 F by P. So from that 2 pi F, which will be given by omega E and T. 2 pi F will be equal to omega, and the rest of the terms we will simplify it and we will write it here. So shaft power will be equal to 2 by P into omega E into Te. Here omega E it indicates the angular frequency which is equal to 2 pi F. Again I am repeat. We know that output power equation is which is equal to 2 pi Nt by 60 for the mechanical output. That N can be written as 120 F by P. So from that we are writing that omega E terms which is angular frequency which is equal to 2 pi F, right. So if you simplify that expression, you can get this shaft power equation which is equation number 7. And if the motor losses are ignored or ideal conditions, the shaft power output will be equal to the input power, which means mechanical power developed will be equal to the electrical power input to the motor. So which will so Pi is equal to 2 by P into omega E into Te, which is equation number 8. From the 8th equation we will write the torque equation, electromagnetic torque developed, which is equal to 2, that is from the 8th equation we are writing it as T is equal to P by 2 into 1 by omega E into Pi. And already we got the expression for input power in equation number 6. We are just bring that equation number 6 here, and we will write that 9th equation as T is equal to P by 2 into 1 by omega E into, we are writing that term Pi from equation number 6. And we are writing the 10th equation. We know that the stator flux linkage which will be constant if the V by F is maintained constant. So voltage bar frequency is maintained as constant. So psi s which is equal to the V by F, that is so angular frequency to the supply voltage. Consider only the magnitude. We are rewriting that above equation as Vs will be given by psi s into omega E, equation number 11. Similarly, we are writing that equation for the Vf, and the synchronous reactance, it can be expressed as omega L, that is 2 pi Fl, so omega E into Ls. We are writing that expressions for direct axis reactance and quadrature axis reactance as omega E into LDS and omega E into LQS. So we'll that is in these equations were considered as 11 to 15, and we will substitute the equation number 11, 12, 14 and 15 in equation number 10, and we will cancel the common terms omega E square, and the common terms as well as, and then we will bring that 1 by omega E inside that square bracket, and we will obtain that equation number 16. Here that electromagnetic torque developed which will be given by 3 into P by 2 into psi s minus psi f divided by LDS into sin delta plus psi s square into LDS minus LQS divided by 2 into LDS LQS into sin 2 delta. Actually the equation number 16 is the torque equation of synchronous motor. But as I initially said, the rotor, that is the rotor part of a synchronous reluctance motor does not carry any field windings. So the field flux linkage which will be equal to 0 for synchronous reluctance motor. So the equation number 16 is applicable for synchronous motor, but we need to obtain the expression for synchronous reluctance motor. So from the construction we will remove that first component which is contributed by the field So we'll remove that component and we'll retain that second component alone. So the electromagnetic torque developed, which will be given by, that is developed torque by the synchronous reluctance motor. Synchronous reluctance motor is T is equal to 3 into P by 2 into psi square into LDS minus LQS divided by 2 into LDS LQS into sine 2 delta. So equation number 17 is the required torque equation of synchronous reluctance motor. Synchronous reluctance motor.